Today we have Alexander, and Alexander is going to talk about shuffle algebra, Macdonald operators, and lattice models. Thank you, everyone, for coming.
Thank you for inviting me and for this opportunity to present this topic that I really like. Well, actually, I recently started looking into this. So my knowledge is a bit limited, and there are a lot more here than I understand. But yeah, let me start. So I will start with some basics of symmetric polynomials, Macdonald functions, and Macdonald operators. And then I will switch to a different language, which is done using the Heisenberg Algebra. So this is an equivalent language, but it uses operators on the Fock space. And after that, I will introduce the shuffle algebra in a slightly general form, but I will only be talking about a particular subalgebra of the shuffle algebra. So this particular subalgebra is isomorphic to the ring of symmetric functions, which is what I will talk about next. And this is, all of this is some background material. So then I will talk about my recent works in applications of this isomorphism of shuffle algebra and symmetric functions. And these applications will be about lattice models. So please stop me. I will be introducing many things. I don't know what is the background of the audience regarding this topic, but there could be too many things being introduced. So please stop me to remind you if you forgot something. So I will start easy with basic symmetric polynomials. So the basic symmetric polynomial here is the power sum symmetric function, symmetric polynomial. Here I take n variables, and this is very simple. We take powers of these variables and add them up. So the next simplest symmetric polynomials, in my opinion, are those which are produced by exponential generating functions. So these are elementary symmetric polynomials and homogeneous symmetric polynomials, and they are generated by these products and their inverses, and this can be written as exponentials. So I'm already using these power sums over here. So this sort of symmetric functions which are produced by these exponential generating functions will play a special role in this talk, and this is why I'm bringing this up. So you can actually check that if you sum the series, you get a logarithm, and then you get this product, and here you get the inverse product. And these functions can be, these polynomials can be written explicitly. So the elementary symmetric ones are just products of variables with non-repeating indices, and homogeneous symmetric ones can have repeating indices here. So then we can take these symmetric functions and start multiplying them, and we will get new symmetric functions. So the power sum symmetric functions, depending on a label, which is now a partition, not an integer as before, but it's a partition. So the thing is that symmetric functions commute, so we can order them, and we only need to consider partitions, so which are sequences of everyone knows what's a partition. And then we do this with all these three symmetric functions. And finally, another type of symmetric function is a monomer symmetric function, where we take products of x's and then we shuffle the indices. So here we start straight away with the label that is a partition, not an integer. And this sum is such that we don't want any integer factors in front, so we need to divide by the symmetries of the partition lambda. So if there are two repeating parts, and then you will apply to different permutations, then you'll get an extra factor. And this monomer symmetric function doesn't contain this extra factor. So let's move on to slightly more complicated symmetric polynomials, which, but first let me tell you that the previous ones, the p lambda, e lambda, h lambda, and m lambda are, they form a basis in the ring of symmetric functions, which is viewed as a vector space now. So we can take any symmetric polynomial in these variables, and we can expand them in either p, e, or h, or m, because these are bases. And we can also grade this ring of symmetric polynomials in n variables by the degree. So we further split this vector space into components of fixed degree. And it's easier to work in a fixed degree component when you want to expand your homogeneous symmetric function. For example, if you have a homogeneous symmetric function. So then we extend the base field, and now I would like to introduce two parameters, q and t, and the coefficients of the symmetric functions will be rational functions in these two parameters, q and t. So first thing that we can do, we can take this exponential generating functions that I used before and modify the exponent. So this is one popular choice. Well, and that produces a function that is known as g. So I'm using notations from the Mcdonald book, and you can see it there. So this is if you want to compute this exponential, it will become a ratio of 2 Pochhammer's, and the way to get it is to expand this 1 over 1 minus q in a geometric series. So we get this symmetric function, jk. This is one way of introducing two extra parameters. And then we start multiplying these different g's together, and we form a basis, which is labeled by partitions. Or alternatively, we can start with the monomer symmetric function and try to modify its coefficients. And the typical one famous example, which is Macdonald polynomial, is where these coefficients are such that they are non-zero if there is a certain condition met on these two partitions, which is an ordering condition, which says that these coefficients are non-zero if mu is greater or equal to lambda in the so-called dominance ordering. And the dominance ordering says that we take partial sums of these partitions, and they have to satisfy this inequality. So this is still a recap from Mcdonald book. And now I would like to introduce Macdonald's polynomials, but for that I need to first talk about the scalar product. So the basic scalar product on the ring of symmetric functions is defined on the power sum symmetric functions, and it's just says that we have this this scalar product, and here we have a coefficient c lambda, which I will be using a lot. Macdonald denotes this coefficient z lambda, but I need z for other purposes. So I call it c lambda, and this coefficient is just a combinatorial factor. You multiply different parts of lambda, and then you take also product of part multiplicities. So mi of lambda will count how many parts equal to I there are in lambda. And we need to multiply the factorials of those. So then we extend this scalar product to the ring with base field f, which is rational functions in q and t. And this is Macdonald's scalar product, which has the same form, but the right-hand side is modified by this rational function in q and t. So then we can state that there exists a basis in this in the ring with q and t, which it's a unique basis, which is defined by two properties. So if we take this scalar product, then it's orthogonal with respect to the scalar product, and it's this basis expands in the monomial symmetric functions such that, so this is normalization 1, and then we have certain coefficients which satisfy this dominance ordering that I mentioned on the previous slide. And these coefficients, they have, if you pick some lambda, they have a definite form. And just to show you an example here, this is how one of them looks. This is Macdonald polynomial of 2, 1, it expands like this. So if you want to actually write this as a polynomial, you will need to write x1 squared, x2 plus x1 cube, and then you need to permute all variables, right? Depending on how many variables you have. And then this is just a simple multiplication of 3 variables. So these are Macdonald polynomials. So now I can go to the operators that act on these polynomials. And these are difference operators. The basic operator here is a shift operator. It depends on variable x, and it just shifts the x variable by q. So that's simple action. And then Macdonald defines an operator, which looks a bit complicated if you haven't seen it before. So it's a sum over subsets of length k. So we take subsets from 1, 2, up to n, and then we take k subsets. So if k equals 1, then the length of subset is 1. So we basically sum from 1 to n like this. So if k equals 1, it's just a linear sum, simple sum. And here we have some rational functions and a bunch of shift operators. So this is how it's defined in Macdonald's book. And these operators, the claim is that they act diagonally on Macdonald polynomials. So this is the explicit action. And you see here that I'm not writing very explicitly this eigenvalue. This is because it actually tells us something. So you see here, this is the elementary symmetric function, k. And these operators, because they are all diagonalized by Macdonald functions, you can multiply them together, and you can form on the right-hand side, you can form any eigenvalue which is E lambda, and which has this special variables specialized to this. This is a common specialization also coming from Macdonald's book and used quite a lot there. So this is one way of writing this eigenvalue, and this is actually one of the crucial things with this talk. And so it tells us that we can take these Macdonald operators, we can consider them as a ring, a commutative ring, and this ring is isomorphic to the ring of symmetric functions, again through this identification of D and E. So now you may wonder, how do other operators look like, which give different eigenvalues. And this is another example, which is Monomer operator. So it has some complicated form. This is just to give you like a taste of what it looks like. It also has this shift operators and some rational functions. But the point is that it acts on Macdonald functions also diagonally, and its eigenvalues are given by this this Qt deformed symmetric functions that I introduced earlier. Just to remind you, these functions are generated by these exponential generating functions. So then we take these symmetric functions and we apply the same specialization here. So we replace the variables with these powers of Q and T. So this is all nice, but how to produce? You can ask how to produce more operators of this type. And to my knowledge, the best language is to use Heisenberg Algebra, in which you will reformulate these operators in using Heisenberg operators. And that will allow us to produce more Mcdonald operators and match them with symmetric functions on the right-hand side. So before I'll do this, I would like to switch to infinite alphabets. So now previously we had n different variables in determinants x. And now we can actually take infinitely many of them. And so we need to modify accordingly every symmetric function that have been introduced. So the operators, they also need to be modified because they actually dependent on n. And you can see here in the eigenvalue this specialization, it depends on the number of variables of the alphabet n. So this is why we need to modify slightly these operators, and this modification is simple. We take certain linear combinations of these d's. So this d is was introduced here, and then we introduce linear combinations of those, very special linear combinations. So this is g, a Mcdonald operator, and this is Monomer operator, and they have some some coefficients depending on Pochhammer symbols. So now if we act with this difference operators on Macdonald polynomials in infinite many variables, then we get similarly looking eigenvalues, but here we don't have this n. So we remove this n. And actually it got canceled with this factor. So we get these two eigenvalue relations. And if you're wondering how to compute this eigenvalues, you need to take elementary symmetric function and expand it in the power sum basis. And then you can replace each power sum, specialized power sum with the right-hand side over here. This is a calculation that you just take this definition and then you take the specialization and you'll find that it has this form. So the eigenvalues, they will be depending on this sort of functions. So here I introduced the length of a partition, which is the number of non-zero parts in the partition. So any questions so far? All good. So let's use a different language to express similar things, which is the Heisenberg algebra. So the Heisenberg algebra here is generated by infinitely many operators. Among them we have positive modes, the positive operators with positive indices, and with negative indices. So this will be, you can call this annihilation operators and this creation operators, as we do in physics. And these operators, they satisfy this commutation relation over here. So it says that almost always these operators commute because of this delta on the right-hand side, and they don't commute only when the indices are opposite. So one of the operators has to be a creation operator, the other one has to be an annihilation operator. And then we get this very specific rational function on the right-hand side. And this is, of course, not an accident because I would like to match this language with the symmetric functions before. So because operators which have the same indices with the same sign, because they commute, we can multiply them together, just like we were multiplying power sums together and other symmetric functions. And we can form these operators which are labeled by partition now. And if you want to multiply these operators with each other, then you can use these commutation relations to simplify these expressions. So now for this Heisenberg algebra, we have a representation, which is a Fock space. It's a space spanned by vectors that are labeled by partitions. And you can build it as a module by acting with creation operators on the lowest vector. This lowest vector is characterized as usual. It has to be annihilated by all annihilation operators, so those which have positive index. And we create this module by acting with creation operators, with the so operators with negative index. So we take these operators with negative index lambda, and then we act on this vacuum state, and we create all vectors of the Fock space. And we can explicitly write down the action of the Heisenberg elements on these vectors. So nu and mu are partitions here. So if we act with negative modes, then we will creating more states. And this is how I denote a union of two partitions as sets. So for example, if we have partition 2, 1, and then we want to do this, then this will be equal to 2, 1, 1. So this is not, this is just putting rows of the Young diagrams together. So this is what this union means here. And if we want to act with the annihilation operator, then we need to remove the parts that exist in this state mu. And otherwise, if there are no parts which are new, also in mu, then it has to kill this vector, so annihilate. And this is taken care of by this binomial coefficient. So this formula here, it's maybe it's not obvious, but it can be explicitly computed using this commutation relations and the fact that this annihilation operators kill the states, the vacuum states. So now we can similarly define the dual Fock space using bra vectors, and they will have similar action. And in this dual space, we can use the two spaces to form scalar products, and they will look like this. So this is again governed by this commutation relation over here. So if I have a state A1, and then I want to compute this, then I will write this as vacuum A1 times A minus 1 vacuum. Then I will need to commute these operators using these relations. And then when A1 meets this vacuum vector, then it gives 0. So there will be only one constant there, and vacuum vectors will give 1. The scalar product. So this takes a bit of time. I think I should rush. So now we note that this Fock space has the same dimension as symmetric functions, symmetric polynomials, and the scalar products match. So this scalar product, it appeared before. This is the Mcdonald scalar product when A's are replaced with P's. And that gives us an isomorphism, which matches these states of the Fock space with the power sums, with the power sum basis in the ring of symmetric functions, the QT ring. So we can use this isomorphism to act with the Heisenberg operators on any symmetric function, and the action is such that the negative modes act by multiplying with the power sum, and the positive modes act by differential operators. So we take a symmetric function, expand in the power sum basis, and then we differentiate with respect to this power sum. So then we can take operators that depend on these Heisenberg elements, and then we can act with them on symmetric functions. And the goal here is to rewrite Macdonald operators using these Heisenberg elements. So the basic most important operator, probably most important operator in this talk, is this one. It's a vertex operator. It's produced by taking a product of two exponentials, which have a very special form. So we have accretion operators in one exponential and annihilation operators in the other exponential. And the reason is that we order them in this way is that if we act on the vacuum vector, then this goes away because it's an annihilation operator. And that simplifies life. So this operator, how to think about this? You can expand this as it's a formal series which packages together lots of operators. So this you can think of this as a Fourier series, and the Fourier modes are these operators. And here I wrote explicitly how one of those Fourier modes looks like. So there is a formula how you can efficiently expand this exponential, and the expansion will run over partitions. And same with this exponential. So in this zero mode operator, we have a sum over two partitions. They run over all partitions, but they have to have equal number of boxes. And then we have these coefficients that we've seen before and some extra coefficient here. And this is an operator that we know how it acts on symmetric functions using these rules. So you shouldn't worry about any convergence issues here, because if you fix two states in the Fock space and you evaluate these operators between two fixed states, you will see that there will be finitely many operators in this sum that are non-zero. Because if you use commutation relations and your operator mu has high index, it will always go through to the state and annihilate it. So you have these well-defined operators with good matrix elements in the Fock space. So what's special about these operators eta, these vertex operators? It's basically how you normal order them. So the normal ordering is just a rule that tells you that if you have operators inside this normal ordering sign, then you need to order them such that on the left you have accretion operators, and on the right you have annihilation operators. So when you have a complicated product of lots of operators and you normal order it, the end result will have the simplest possible action on Fock vectors, because these operators will annihilate the vacuum state. And the main property of the operators eta, and that they normal order at the expense of these rational functions. And so just to remind you that these operators, they depend on the negative modes and the positive modes. So if you take two operators, if you multiply two such operators, you will have negative modes, positive modes, negative modes, positive modes. So you need to exchange two exponentials. You need to commute them. And the way you compute this is by using the BCH, the Baker-Campbell-Hausdorff formula, or similar. It's a good exercise, but I'm not going to do it here. So we can take these operators in different orders, so eta W, eta Z, and normal order them again. And then we will find that these operators, you can commute them at the expense of rational function over here. And this rational function, it's a cubic polynomial in W and Z. And if you look carefully over here, we're switching the parameters. And if you, for example, if you get rid of these two factors and you consider this rational function, then this should remind you of commutation relations that appear in quantum finite algebras. SL, UQ, SL2 hat, for example. So this is not a coincidence, and this sort of relations will keep appearing. So now, why do I introduce these operators eta? It's because they act on Macdonald functions diagonally, and the precise connection with the E operators, the Macdonald operators, is this. And again, we can write explicitly the eigenvalues using symmetric functions. So in this case, eta 0 produces the operator E1. And the way you prove this, you need to act in the power sum basis and use lots of tricks. And it's a technical calculation. And then after this calculation, you actually prove that you match these operators have the same action. So now how to produce higher Macdonald operators? So far, this was just E1. So to produce higher Macdonald operators, we reinterpret this, the modes. We need to use integrals, residues. So in this case, E1 is a simple operator, and we just take, we can say that eta 0 is a constant term of the full operator eta. But for higher operators, we need to introduce a rational function. It's given explicitly over here. And this rational function will appear as an element of Shuttle algebra. So if we use this rational function in this sort of integrals, so it's written explicitly over here, then we will produce operators in the using Heisenberg elements, which sit inside this normal order product. And these operators will again match the Macdonald operators. So here I modified the constant in front of this integral, so it takes care of this factor that appeared before. So the message here is that now we can produce, using integrals like this, and this basic vertex operator, we can produce Macdonald operators. So we match these eigenvalues. And the way you prove it, you start with the known relation between eta 0 and E1, and then you try to recursively prove that ENs match with Macdonald and Macdonald operator. So this is a technical proof, but once you're done, it actually leads to many things. So you see now that we reformulated the Macdonald operators in this language, and we would like to keep going. But in order to write new Macdonald operators in this language, we need different kernels. And all these kernels, they actually form a ring by themselves. So they form a ring, a commutative ring, which is a commutative shuffle algebra. And this is what I'm switching to right now. So again, we need two parameters, Q and T. And for simplicity, we use three parameters in the shuffle algebra, but only two of them are independent because of this relation here. So we use Q1, Q2, Q3. And this shuffle algebra, AN, it contains elements which have this special form. So we take a symmetric function, a symmetric Laurent polynomial, and divide by the square under mod. So this is how shuffle algebra A look like. And in addition, we require that this symmetric function in the numerator, it satisfies the so-called will condition. So this is a condition which appears when we have three variables. So when n is at least equal to 3. And it says that we need to take three variables z, and we need to specialize them in this way. So we use these parameters Q1, Q2, Q3 to formulate this will condition. And so this has to hold, or this has to hold. And then the numerator has to vanish. So maybe it doesn't give you much insight, but this is actually an important condition which brings this space, which puts significant restrictions on the space. And, so maybe an example. So if there are 0 variables, then this is trivial. It's just the base field. If there is 1, then there is no van der Monde. So we only have the numerator, which is a symmetric function. And we can take any of those powers of z. And more interesting elements live in when there are 2 variables. So you see here this van der Monde squared. And the numerator is a symmetric function in 2 variables. And you can see that if you set z1 equals to z and z2 equals to q1z, then this will vanish. So for example, if I equals to 1, it will vanish obviously, but if I equals to 3, then you need to use this relation. And then you will find that either this or this vanishes. So this element satisfies the Wheel condition. So now what makes this an algebra is a product. So this is called Shuttle product. And the most important ingredient in this Shuttle product is this rational function. It has, it's also expressed in terms of this function g, which I introduced earlier. So the way I introduced it earlier was with using q's and t's, but q1, q2, q3 are related to q and t. So we produce new Shuffle algebra elements by taking 2 Shuffle algebra elements and then symmetrizing them over all possible arguments. So if f had k arguments and g had l arguments, then we need to shift the arguments of g, multiply by this rational function built from these guys, and then we need to symmetrize over all possible ways of permitting the arguments z. So this structure here is such that the end result also satisfies the Wheel condition. So remember that these f's, they have to satisfy the Wheel condition. They will satisfy them if you choose this zi, zj, zk, ijk to be inside this first set, then f will satisfy the Wheel condition. If you choose them to be in the second set, then g will satisfy the Wheel condition. And if you choose them to be partially in one set, partially in the other set, then this will make sure that the Wheel condition is satisfied. And basically the Wheel condition determines this form. So this is fixed by the requirement that the Shuffle elements have to satisfy the Wheel condition. And here is an example of a Shuffle product. I'm just substituting this W into this simple case where k equals to 1 and L equals to 1. So we need to take this function and multiply by this one where 1 becomes 2, and then take permutation. So there are just 2 terms in this case. Then now we have multiplication, and we can take Shuffle algebras with different number of arguments and multiply them together and produce new elements and produce larger elements, basically. So we take basically the whole space with all possible number of arguments there. And the claim is that this Shuffle algebra is generated by the degree 1 elements. I mean, degree is the number of arguments. So this is a theorem and it's quite non-trivial. But yeah. So another interesting statement about these generators is that they, under the shuffle product, they satisfy an interesting commutation relation. So if we take a generating function of these elements, so this it's just a delta symbol, formal delta function. And if we use shuffle product between two such delta functions, then at the end of the day, which is actually not a hard calculation, we will arrive at this commutation relation. So if you want to switch this V and U, then you will get on the right-hand side, you will get this. And this already appeared once. This appeared as the commutation relations of the two operators eta, the ones that were giving the Mcdonald operators. So this relation appears for the second time in this talk, but in a different context. So now in this big shuffle algebra, there is a subalgebra of elements whose degree is equal to 0, which means that the degree of the numerator is equal to the degree of the denominator, the square of under 1. And in addition, we need to set we need to say that all these elements, they have certain limits, they coincide. I don't want to talk about this. Will take a bit of time. So there is some extra condition that we need to impose, and then we get a subalgebra of degree 0 elements. And let me show you how it looks. So degree 0 elements in 0 variables is simple, and then basically the same thing, but you need to say that there is one variable. So is z1 to the 0, to the power 0, because it has to be degree 0. And then if we increase n, then we can, for example, we can look at these elements. So these are the same elements, basically the same elements that I showed before in the examples. And so we have square van der Waals, and we have numerators which satisfy the will conditions in this, which is not very difficult. And we have three such elements because we can choose Q to be either, this parameter to be either Q1, Q2, or Q3. And these are most important elements, perhaps most important elements in the shuffle algebra. And, right. So what are the properties of the shuffle algebra? Well, of this subalgebra, rather. If we take n, this degree 0 components of the shuffle algebra in n variables, then the claim is that the dimension of this space is equal to the dimension, to the number of partitions of n, which is a good sign. And the way to prove this is to show that epsilons, if we take products, these are actually shuffle products. If we take shuffle products of these epsilons, then they will produce elements that depend on the partition lambda, and these form bases. So now I'm producing again basis elements. So first there was basis and symmetric functions, then Fock space, the basis there, and now I'm doing shuffle algebra version of basically the same thing that I was talking about before. So these epsilons, they produce bases labeled by partitions, and the dimension is good. And then the next claim is that this algebra is commutative. And the way to prove it is by an explicit computation using specializations. It's a bit technical. And you need to show commutativity of two such elements. So when you show this, then you can say that this algebra is commutative because these are basis elements, and this will hold for all elements. So now we have this subalgebra which is commutative, and we can introduce an operator that will help us to form the the isomorphism, because this again looks like the ring of symmetric functions. And the operator that we need is, it looks familiar if you remember the Macdonald operators that I showed before. So we take, again, this vertex operators eta, take their normal product, and we take these denominators given by these basic elements, Q1 and depending on Q1 and Q3. Just to remind you, this was Q inverse and Q3 was equal to T. And we integrate this with various kernels, which come from the shuffle, the commutative shuffle algebra. So the message here is that we built operators with the kernels whose kernels are shuffle algebra elements. And then the claim is that we can separate this integral like this. So if we take two shuffle algebras elements, f and g, then we can just multiply these operators together. So that's a very important statement, which says that this map is compatible with the shuffle product. And one immediate consequence of this says that these operators OF, they are commutative, because when you pick f from the commutative algebra. So this produces a ring of commuting operators again. And this is what we wanted. So if I pick this kernel f to be one of these are shuffle algebra elements. If I pick it to be Q1, it will produce the Mcdonald operator. So it's the same as the formula as I wrote before. But then the question is how to produce other Mcdonald operators. So if we pick the two other shuffle elements in this integral, then we will produce new Mcdonald operators. And the action of these new Mcdonald operators can be computed, and it uses identities in symmetric functions, simple identities. And through the action of these operators on Macdonald functions, and by looking at their eigenvalues, we can state the isomorphism. So if we take an operator with this kernel, then the eigenvalues will be given by the elementary symmetric functions. If we take a different kernel with Q3, we will get the J's. The eigenvalues will be specializations of this J's. And finally, if we take this one, we will get a new symmetric function. I mean, I knew that I haven't introduced it. So this symmetric function is also given by an exponential generating function. So this looks slightly like G, like the one for G, but G had one over here, and here we need, for this one, we need Q. So how much time do I have left?
You have about 10 minutes.
10 minutes?
Yeah, sorry, yes.
Yeah. All right, this should be enough. Now applications. Applications of shuffle algebras. So the first type of applications is producing new shuffle algebra elements, which are not just simple products. I mean, these epsilons, they were given by, I'm just reminding you, they were given by the simple products. Of course, if you want to shuffle multiply them, you will get complicated outcomes. But another way of producing shuffle algebra elements comes from lattice models. So we can take the 6 vertex model, which typically presented using arrows, which are pointing towards a vertex or outwards. So there's a conservation of how many arrows you can direct into vertex and how many arrows you can direct outside. And if you count number of cases, it's going to be 6. So I'm guessing the audience is familiar with this stuff already, so I'm not going to go through this in too many details. But one thing I want to say that we can view this using lattice paths. So I can replace with the path and up arrow, pointing arrow with the path as well. So here I will draw on top of these pictures what we get. So this red paths that go through, they propagate through the vertex, basically. So this one is empty. This one goes like this, and this one is turning. And just for convenience, I will this will be an empty space. So there is no path. This is a vacant space where there could be a path, but there is no. And using these vertices, we can produce partition functions. Popular domains are these square domains. And I guess you've seen this before. So using this lattice path formulation, we can also reformulate this as paths that go from that go to the right and up, or vice versa, depending on your preference. So I can draw here this configuration in the language of lattice paths. I can draw like this. So this is a particular example of lattice paths that one can encounter with the 6-vertex model. And it has it's convenient to use to encode these weights and configurations using the R matrix. And it is common to pick this R matrix to have this parameterization using the spectral parameter X and an additional parameter T. And this R matrix satisfies the N-Baxter equation. Looking here, and this equation takes place in the temporal product of three vector spaces C2. So this R matrix, from the point of view of quantum groups, it appears from the considering the fundamental representation of UTSO2 hat, or UT to the 1/2. I'm not sure. This should be T or T to the 1/2. So now we have statistical mechanics models using this R matrix and 6 vertices. And we can build all kinds of partition functions on all possible domains. So let's take a particular case of these partition functions. And this is a common choice, which is the domain wall partition function. So we take a square domain and we will consider in this domain lattice paths that start on the left boundary and they propagate to the top boundary. And you can interpret it this way. So you consider this sort of partition functions, and the partition function is the sum over all possible configurations which satisfy these boundary conditions. So one example would be this configuration. So I'm just connecting the left states with the top states. And now we compute this, but using the Boltzmann weights of the R matrix, these Boltzmann weights, and we attach. So this will be a single R matrix, and we attach spectral parameters to the lines. So this is. I'm not explaining this with details, but I'm guessing that the audience knows a bit about these things, or actually quite likely this by now. And if we calculate this partition function with this inhomogeneities, then we will get a determinant. So this partition function is known as Krepin's domain wall partition function, and the outcome is the determinant of either given. So I write this determinant over here, So it looks like this, and it has some normalizing factor. So the nice thing about this determinant is that we can take this y's and then we can specialize them to be proportional to xi's. And the proportionality factor is taken here to be q. And just to remind you, we are using t over here. So that's a different, it's not q. So this is, so we had one parameter t over here, and now we're introducing a new parameter q through this special case. So this does not trivialize this determinant. It's still a determinant. So I'm replacing x's with z's now. So we still have a determinant. And here I give the normalizing factor. And this element here, it satisfies the real conditions. It can be checked. And it also has a 0 degree and it satisfies those limits. So this element lives in the Shuttle algebra, AN. And you may wonder what sort of operator does it produce? Because we can take every Shuttle algebra element, insert this into this integral, and act on Macdonald functions. And the answer is that it produces the homogeneous symmetric function. So the specialized isomorphic determinant is, as a Shuttle algebra element, maps to the homogeneous symmetric function, which is a bit surprising. So that this is interesting fact, and it can have some applications, for example, in integrable probability, Mcdonald processes. So we can take this a bit further and start coloring this lattice paths, and so we will switch to UQGLN models or UTGLN models. And the R matrices now, their H states are labeled by colors of the paths. That's why I wanted to introduce the paths. So we can take a path and now we can color this path by some different ways. But this will be typical configurations. And the indices I and j, they just label the colors. So we can label the colors from 0 to n-1 or n to n. So now this is just given explicitly the R matrix that satisfies the Young-Boxer equation. It's a compact form to write this R matrix. And the claim is that we can use this R matrix, place them and consider colored paths on square domains. And if we choose cleverly the boundary conditions and the same specialization as before, then we will produce more Shuttle algebra elements. Well, actually, I have in mind one non-trivial, highly non-trivial element and one trivial element. So this is work in progress with the post interesting. So one interesting application of this is in algebraic geometry, because it turns out that these Shuttle algebra elements also show up as Hilbert series of interesting schemes. So this is a second application in the lattice models. And the third application, I guess I don't have much time, but the third application is has a completely different taste. So in this application, you take partition functions, but it produces an R matrix itself. So in this application, I'm considering an extension of the 6-vertex model. So now the 6-vertex model, to extend it, I need to replace the labels by Young diagrams. So I'm replacing these arrows or lattice paths by single box like this. And then I'm allowing these H states to be any Young diagrams. So if you want 2 boxes, you will have these states and their rotations. Or you can look at any Young diagrams. The only rule here is that the number of boxes on the, let's say these are incoming Young diagrams, has to be equal to the number of boxes of the outgoing. So the Young diagrams, they come together, break apart, and then they form another pair of Young diagrams. And this will be new vertices, and they will have Boltzmann weights. And you want to ask, what are those Boltzmann weights such that this is an R matrix, so such that it satisfies the n-Baxter equation. And one way of producing this model is by taking a Fock representation of a quantum toroidal algebra, EQT-G01. So this algebra depends on two parameters. I don't want to go through this algebra because I don't have time, but the point is that one of the elements of this algebra in the Drinfeld representation, it satisfies the same commutation relations that appeared before. So we saw this relation where these operators were etas. We saw these relations where these were delta functions and the product was shuffle product. And now these are defining relations for this quantum product. A bunch of relations here, and there is a co-product because it's a Drinfeld quantum double. And this algebra has an R matrix that commutes with the coproduct and satisfies the other relations. And we can calculate this R matrix in the Fock representation. So this algebra has a Fock representation. In this representation, basic operators, they're written as the vertex operators that appeared before. So the etas, and this psi is similar to eta, but it's similar looking, but slightly different. So now the form of the R matrix, it comes from the pairing of the quantum double of this algebra. And it has a simple exponential factor here, and then there's an interesting part, which is R bar here. And this R bar is given by another integral operator on the shuffle element. So this shuffle element, it's the third one, meaning that the first one was giving the Mcdonald operator, the second one was giving Monomer operator, and this is the third one. And by knowing the eigenvalues of this operator, we can produce matrix elements of R. And this will be the spectral parameter dependence, basically, which is given by the eigenvalues of the Mcdonald operator of the shuffle element. And this is it. This is, I'm done. And okay, so just to mention, this is work in progress with Andrea. And yes, so now I'm done.
Okay, let's thank the speaker. Oh. Let's thank the speaker. 2 devices. And there is a feedback loop. Okay, let's stop recording.